Hi everybody. Today we're going to talk about data conceptualization, measurement, data types, and data sources. Our learning objectives for today: first, we want to talk about what is measurement and define it. Then we want to talk about how do we measure. Then we're going to talk about how do we measure an abstract concept and then operationalize that concept. We'll talk about what level of measurement you should use. We'll talk about how should indicators of proper measurement be constructed and the difference between an indicator and a variable. And then we'll talk about how do we evaluate different measures. If you're having a difficult time seeing the slides on the screen here because of the projection and resolution, please make sure you download the slides off of the web and follow on the lecture notes and the lectures themselves as you go through this video. Alright, let's talk about defining measurement. Measurement is defined as the assigning of numbers to some phenomenon that we are interested in analyzing. Basically, to facilitate the use of mathematics in studying and describing phenomena. In the hard sciences, data are commonly available for measuring phenomenon, but in the soft sciences and the social sciences, it's not the same way. So often we have to look at other ways of measuring in the soft sciences and the social sciences. It's important to note that. Without quantitative data, like for example in the social sciences, we often use categories or classes as the way that we perform measurement. For example, a study that looks at white versus non-white individuals or female versus male individuals. So often we'll have other types of studies that don't have hard data, and we're looking into categories and classification systems as well. The particular system, and this is important to note, the particular system of measurement that you use is not as important as a consistent set of rules that you use in measurement. For example, Fahrenheit or Celsius to measure the effect of temperature on productivity is not as important as establishing that temperature does have an effect on the work environment, right? So we can use Fahrenheit, we can use Celsius, but what we're trying to look at is especially the measurement of temperature on the work environment. Let's talk about measurement theory a little bit. Measurement theory assumes that a concept representing some phenomenon that the analyst is concerned about cannot be directly measured. So we're typically using data or indicators of that phenomenon to try to measure it. We can't directly measure it in these cases. Let's give you an example of productivity again in construction. We would assume that productivity is simply a measure of the amount of time it takes to install one item of work during the construction process. But there are many other factors involved, obviously. We call these indicators, and these indicators they need to be considered when we're measuring productivity. For example, weather and temperature, crew size, accessibility, safety, and the list keeps going. We'll continue with the productivity example in construction here as we go through the slides. Therefore, we often need to define a process that will measure the concept, okay? And that's called operationalizing the concept. So if we break it down into conceptualization and operationalization, conceptualization is the process of making abstract ideas more precise or specific. In very basic terms, it's defining a concept. Okay? Operationalization is the process of specifying the operations required to measure a particular concept. So when we move from concept to defining the process that defines the concept, that's where we're moving from conceptualization to operationalization. Let's just get into conceptualization first though. Okay? The concept is the basic building block of research or theory that abstracts or summarizes a particular characteristic or aspect of a class of events. If you want to look into more detail, I've taken these definitions and concepts directly from different sources, and they're located at the bottom of the screen and of your lecture notes. For example, if we talk about productivity and the concept of productivity, we would ask questions like, what events or characteristics constitute the concept of productivity in construction? They're often derived from different units of analysis. So here are some examples of units of analysis. Individuals might drive productivity. Groups, we call them crews often in productivity. Organizations, let's say there's subcontractors that might drive productivity on a site. Time, location of work, type of work, is it residential, is it commercial? Division of work, in this case I'll give you an example of 3300, concrete, but it could be many other divisions of work. Safety can drive productivity, so it continues, the list continues. But we need to be aware that there are all types of different units of measurement, and these at the conceptual stage are called indicators. All right, once we move into operationalizing the concept, right, defining the process that will define the concept, it's really just a statement that tells the analyst how a concept will be measured. It needs to be very transparent, very straightforward typically. We need to be able to say these are the ways how we will define the process around defining that concept, okay? Often these can be written actually as equations as well, and you'll see that later in the work that we're doing. An indicator, which is really just a form of measurement, it's the measurable aspect of our concept. So the number of individuals in our unit of analysis in the last slide, for example. You can have a single indicator, which is relatively limited in its ability to perform analysis, or you can have multiple indicators, okay? I'll go back to the construction productivity example. How might we operationalize a study on productivity in construction? Well, for example, we use indicators such as measuring daily, weekly. We're timing the work. We might look at the number of people involved in the process, when we're looking at productivity and so on. It's important to also understand the concept of error and the error term in all of the work that we do in analytics. In the case of indicators and understanding concepts and operationalizing concepts with indicators, indicators are not typically a complete measure of a concept. They contain error in that measurement, always, inherently. It's very difficult to find an error-free indicator. So, we can assume the following equation typically. An indicator equals the concept units of measurement, whatever the units of measurement we're talking about, plus some error term. So let me give you an example of why that's important. A good indicator has a small amount of error term, and a poor indicator has a large amount of error or error term. And sometimes we use certain ways of testing for error to see whether the indicator is adequate or not. An example, temperature might be a poor indicator of productivity if the work is inside a climate-controlled building. Pretty straightforward. So we can't always assume that temperature is a good indicator of productivity, for example. We also have to work with validity when we talk about measurement. A valid indicator accurately measures the concept it is intended to measure. Often you will test for validity as well when we get into statistics and other forms of measurement. But here I just want to make sure you have some basic concepts and terms around validity. We have a face validity is one term of validity. That's just where a manager accepts the validity of the indicator due to experience. We have consensual validity. That's where numerous persons in different situations accept it as valid. For example, you might go out and talk to a panel of people and they might say, yes, this is a good indicator for productivity. So you go ahead and you use that when you're working to study productivity on a construction site. Correlational indicator correlates strongly with other indicators. So we have good indicators. We find through doing some research or looking on the web or other places, reading in journals, that there are other indicators that serve as good. They have a correlational relationship with certain indicators as well. So we want to bring those in. The other way that we can look at correlation is through statistical analysis, which we'll talk about much later in the class. And then we have predictive. That's where the indicator can actually correctly predict a specified outcome. These are very detailed and often hard to come by. All right, another part of measurement besides validity is reliability. A reliable indicator consistently assigns the same number to some phenomenon that has not in fact changed. So if we want to look at the number of cars that are passing an intersection, for example, and we have people who are changing in their measurement of that, well, it's not a very reliable indicator to use people who walk by the side of that interchange. We have to have some kind of a constant, non-changing way of knowing that the count of cars in that area is reliable. There are major threats to reliability: subjectivity, a measure that relies on the judgment of the person measuring it. So if we have measurement that's taking place, for example, direct observation, that you might be watching processes in place, but you have your own biases, that can be a big problem. And that's a subjectivity threat to reliability. Also, survey respondents sometimes have their own biases as well, and we need to know about that. Or that the reliability, that the measure has lack of precision. And that means that it just incorrectly represents the sample. For example, housing quality often is measured based on these categories: good, above average, average, and dilapidated. Well, when people go to define the quality of their house, or you have someone who's looking at a house and they are checking off the quality of that house on a survey, how do they really know what good versus above average versus dilapidated means? Right? So it can have a lack of precision. It can be difficult to gain a lot of good information from those surveys. Alright, so let's now talk about how do we measure. In data analytics, we typically need to convert the basic information of a problem into data, right? So, we commonly use levels of measurement for collecting and operationalizing data analysis. It is important to remember that the level of measurement of data and type of data, will define the analysis you perform, right? All of these different considerations will often drive the type of analysis that you can perform. If you don't have data that support a certain type of analysis, you're not able to do it. Okay? But we are typically trying to convert basic information of a problem into data. And that process, in operationalizing the concept, we're moving from indicators typically to variables. We'll talk about that more. But there are levels of measurement. The precision, and the way we define levels of measurement is the precision inherent in the measurement of different types of variables. I'm going to repeat this at the top of each slide just to make sure that you understand that that's the definition of levels of measurement. One highest order, which Harrington in your previous reading calls variable data, is called interval measurement. Okay? Measurement is based on a unit or interval that is accepted as common standard and that yields identical results in repeated applications. Okay? It's quite precise typically. It can be expressed in terms of distance between attributes as well. You can ask the question, how much more or less? And that could be an interval measure. Here's an example: weight. Right? A person weighs more or less than another person. Height or distance. These are interval measures. They're high precision, and we can rely on their precision. The next level down, again, I'm defining again levels of measurement, is ordinal measurement. Okay, this level of measurement, it's possible to say that one phenomenon has more or less of a given characteristic than another, but it is not possible to say how much more or less, right? They can be rank ordered, and you can ask the question, is it more or less, right? Examples: agreement. You fill out a survey, people want to know, do you agree, do you highly agree, do you not agree? The likelihood, are you highly likely to use this again or recommend this? And then satisfaction. In surveys where you fill out satisfaction surveys, highly satisfied, satisfied, not satisfied. And here's an example of an ordinal measure that you might see from a survey response. What we see here is we see the different possible answers, and we see names of people, and we see their ranking on satisfaction based on this ordinal measure here. Okay? And then the lowest level of measurement that I want you to know as a definition is the nominal measure. Harrington calls this, in your reading that you did previous to this class, attribute data, right? Totally lacks any sense of relative size or magnitude. It allows one measure only, whether a phenomenon is different or the same. It's mutually exclusive. It's unordered categories typically. You could ask of nominal measures, which category is it in? You can ask questions like that. Okay? Here's an example. Gender, religious affiliation, employment. And I'm giving you a sample of what someone might respond to on a survey. Are they full-time employed or part-time employed? You could have 3 here and say not employed. But here we're seeing, and that should say employment here. and we're seeing numbers based on this nominal measure of whether they're employed or not. 0 meaning, zero should be 1, maybe we'll change it this way. We'll make this 0, make that 1. So 0 being full-time employment and 1 being part-time employment. Okay? In this case, we have a nominal measure of this group of people, and we can categorize them based on that measure. Now keep this in mind for later. I'm going to go back to these measures into a larger chart we're going to talk about in just a little bit. Alright, if we look at the indicators, we need to also focus the terminology that we use with them. And this is where I was talking about before, where we're moving towards the information and the measures that will specifically be inside the operationalization of the concept. So once an indicator has been operationalized and measured in a sample, like we just did in those previous samples where we said part-time or full-time, for example, it's now called a variable. We've moved from an indicator to an actual variable. There are data behind it. A variable assigns numerical scores typically, for example, 0 to 100 or even more. It doesn't have to be between 0 and 100. And categorical labels. For example, you can use female, male, you can use employed, unemployed as well. Eventually, those will be turned into numbers as we do more and more analysis as well. And it assigns those measures to each observation in a sample. In the previous slide, each name would be an example of an observation. It just means the measuring of case by case is what it means. Okay, so variables are often divided into two types. We have dependent variables typically, and we have independent variables. Especially in analytics, and then as we move into statistics, this becomes really important. A dependent variable is explained through dependencies on other variables. All right, so productivity is dependent on these other variables would be an example of how we could describe productivity as a dependent variable. An independent variable is thought to affect or have an impact on the dependent variable. So there has to be some kind of relationship there. I'm going to walk through an example here so you can see different ways we look at these. So in other words, dependent variable, we typically use this abbreviation for dependent variable, equals, as an equation, independent variable, for example, IV1, IV2, 3, 4, and so on. Okay? To give you an example based on what we've been saying for the whole lecture here, productivity is dependent on what indicators, all right, and how do those indicators become variables for testing? Now I will give you an assignment outside of class that asks you to look at a different concept and looking at the indicators that you think would be appropriate for that concept, and then as we operationalize it, how they become variables for testing as well. But in this case, we use dependent variables and independent variables to create a hypothesis that we will test mathematically. And that's where we're going in the next slide. So, here's our hypothesis. Productivity is a function. In other words, it depends on employment satisfaction, employment status, time wasted, and number of breaks. Right? So this is just a hypothetical example here, but we are saying in this hypothesis that these four independent variables, and these could each be listed as, right? And this could be listed as IV1, right? Here we have the cases, right, or the observations. And notice what I've done here. I've changed from names to cases. And now we have anonymized each name, and we're treating them as a case of data, right, at each observation. So Jones becomes employee 1. Patterson becomes employee 2. And here we are looking, we've added the data by each case or by each observation from the previous example that I talked about. But we've also added time wasted on the job in terms of minutes and the number of breaks that case, which was based on a person that we observed, might take. Okay? So let's continue with this same thread here, with the hypothesis generation. So the hypothesis is productivity is a function. It's dependent on employee satisfaction, employment status, time wasted, and the number of breaks. We write this as an equation by saying the dependent variable, productivity, is a function. We use that shape right there. Okay? It's a function of the independent variable number 1, which is employee satisfaction, plus independent variable number 2, which is employment status, plus independent variable 3, which represents time wasted, plus independent variable 4, which is number of breaks, plus, and I mentioned this before, we have an error term typically in all of our functions, right? This is meant to account for the fact that there is a level of error in each one of these that we know is inherent in the process, and it becomes part of our hypothesis and our mathematical equation. All right, next I want to quickly talk about sources of data where you might go and look for information to help define a concept, operationalize a concept in the construction industry. We have two types of sources. One is primary data. That's original data gathered from the original source, okay? So you are an employee within a company. You are going and gathering data yourself where you're watching and observing. That's primary data, okay? You're watching and observing people and their productivity. For example, we might directly interview employees as well regarding their satisfaction. We are gathering information directly from them. There are secondary data sources as well, and that's where information is already available, it's been gathered by others, and it's been placed up maybe on a website or it's been handed to you. But what's important to know about that, right, is there might be another purpose for why that information was gathered. But here's an example. A consultant watched your workers and reported wasted time on the job for you and gives you that information. What you need to know is that there are advantages and disadvantages to both. When it comes to primary data, you have to watch out about the bias that comes along with the people who are directly observing and collecting the data. When it comes to secondary data, you need to understand the purpose of the data in the first place. For example, if you use census data, you'll need to go and look and see how they actually collected the data, how they merged the data, how they made the data available to you, because they give you notes that say, listen, these data are not appropriate for this type of use, but they're very appropriate for this type of use. Or when you look at this, you need to look for deviations in the information and where there might be errors, right? So they give you information that tell you how to work with the data. But you need to be very cognizant of that. We're going to talk about RS means a lot in construction data and analysis. They have their own purpose, and they are a form of secondary data as well. And here are some sources that I'm giving you where you might go look up data. But from the primary data standpoint, to give you examples, you might do direct observation, or somebody that you employ, a consultant might do direct observation, in the example of productivity, watching your crews work. You might have surveys that you employ. You might use interviews as well for primary data. Secondary data sources, commonly in this course and in the construction industry, we're going to use sources like RS means. And it's difficult probably to see the link here, but you can see it on your slides if you download the lecture notes. Census data, a lot of important information comes from the census. Bureau of Labor Statistics, you can learn a lot about a market that way as well. And then here's an example of NIOSH as well. Another one that I might put up here is ENR, Engineering News Record, which is important especially for infrastructure and data around infrastructure. That concludes the lecture for today. If you have any questions, please contact me, and I look forward to hearing from you.